Geochronological methods let us put time on landscapes. We will build intuition for three pillars used in active mountain belts: thermochronology, cosmogenic nuclides, and optically stimulated luminescence. Each operates on different physical principles and timescales, and together they cover the spectrum from recent events to millions of years. First, thermochronology. The idea is simple and powerful. Minerals record the time they cooled below certain temperatures, called closure temperatures. As rocks are brought toward the surface by uplift and erosion, they cool. Cooling ages, therefore, tell us when a rock passed a particular temperature window. We will draw a crustal column with depth and show key closure isotherms for zircon helium, apatite fission track, and apatite helium. Suppose our sample has an apatite fission track age of 1 million years and a closure depth near 4 kilometers, which corresponds to about 110 degrees Celsius in a normal geothermal gradient. The average exhumation rate is depth divided by time. 4 kilometers in 1 million years is 4,000 meters per million years, which is 4 millimeters per year. In practice, we combine multiple systems like zircon helium, apatite fission track, and apatite helium to reconstruct a thermal history through time. Younger ages near range crests often indicate very rapid exhumation, but interpretation must consider heat advection and evolving geothermal gradients at high uplift rates. Next, cosmogenic nuclides. High-energy particles from space strike mineral lattices near the surface and create rare isotopes like 10 beryllium, 26 aluminum, and 36 chlorine. The concentration builds up while a surface is exposed, which lets us date when it was uncovered or infer erosion rates if the surface is slowly wearing down. If production is roughly constant and erosion is negligible, the buildup follows an approach to saturation. N of T equals P over lambda times 1 minus e to the minus lambda T. Early on, it is almost linear. Much later, it asymptotically approaches P over lambda. A classic tectonic application is to get fault slip rates by dating offset landforms. Date the surface with cosmogenic exposure, measure the offset, and divide. For example, 30 meters of offset and 6,000-year age gives 5 millimeters per year. Cosmogenic nuclides can also estimate basin-wide erosion rates. Analyze river sand for 10 beryllium and invert concentration to an average removal rate. Care is needed for inheritance and shielding, but with multiple samples the rates are robust. Finally, optically stimulated luminescence, OSL. Sunlight resets the luminescence clock in quartz or feldspar grains. After burial, the signal builds with time due to natural radiation. To date a deposit, we measure the stored dose and divide by the dose rate to get the burial age. The burial age equals the equivalent dose divided by the dose rate. Field sampling is done in darkness, often by driving a light-tight tube into a fresh section, then measuring dose rate from uranium, thorium, and potassium. In summary, these methods convert landscape shape into time and rates. Thermochronology reveals million-year scale exhumation histories. Cosmogenic nuclides time exposure and quantify erosion or slip rates over up to 1 million years. OSL dates the burial of sediments over the last few 100,000 years, even when organics are absent. Using them together lets us build complete timelines from recent events to deep time. Thanks for learning. In practice, multiple samples and inverse modeling help address complexities like changing rates and heat advection. The key is to match the method to the question and timescale.